So it looks like the answers are pretty spread out across A, B, and C. So the thing I would think about, so this one is kind of funky. We'll talk about it in a minute. Well, let's actually talk about this limit. So to see what that limit is, the only really, at least in my opinion, the only really good way to do it is to actually see what the graph of the natural log of x looks like. So we look at the graph of, is this my good pen? Of y equal to the natural log of x. It's got an x-intercept at 1, 0. And as we see, as x approaches 0 from the right, as the x values go this way, the y values go down to negative infinity. So it is true that this limit here is in fact negative infinity. It's also true that this limit is as well, because I said they're the same, but we can actually kind of use this graph to help us figure out this limit. So if we're approaching 1 from the left, the natural log of x, well, we can erase. So now if we're approaching 1 from the left, well, the natural log of 1 is equal to 0. So we've got a 1 over 0. We know when we have a non-zero over 0, the answer is going to be some sort of infinity. And in this case, since we're approaching 1 from the left, the natural log function is negative when we're just left of 1. So that we're in fact getting a positive divided by a negative. Right, we can write it like that, a 1 divided by a very small negative number, but a positive over a negative is going to be negative overall. So this is also going to be negative infinity. So both of these limits would be negative infinity. What does that mean graphically? Well, what it means is that, well, obviously for this one, right, as x goes to 0, this goes to negative infinity, and we have a vertical asymptote there. So when you take a limit as x approaches a real number, if that limit is equal to some sort of infinity, it does mean graphically that we have a vertical asymptote. Similarly here, I don't really know what this graph looks like, but if we graphed it, we would definitely get a vertical asymptote at x equal to 1, because as we approach 1, the limit is some sort of infinity. Sorry, one sec here. So, yeah. So what I really want to say about this is that we know, and there's kind of lots of ways to know you have vertical asymptotes. Sorry, I thought I erased this. What unprofessionalism. So here's a question. Does this function f of x equal to, let's make it real straightforward, 3 over x minus 2 have a vertical asymptote? Yes, it does. Where is the vertical asymptote? I'm not sure what scared you, Gabriella, but I'm sorry if I scared you. So does this have a vertical asymptote? Yes. Where is it? At x equal to 2. How do we know? Because if you plug in 2 for x, you get division by 0. I should say you get a non-zero number divided by 0. So to me, that's enough to be like, yeah, we know we have a vertical asymptote there. Now, more precisely, we can say we have a vertical asymptote there because if you take the limit as x approaches 2 from either side, let's approach 2 from the right, of 3 over x minus 2, you're going to get 3 over a 0. And when you have division by 0, you're going to blow up to some sort of infinity. In this case, it's a positive over a positive, so that's going to be positive infinity. But once your limit as x approaches a real number is some sort of infinity, that means vertical asymptote. We don't even have to do the limit from the other side, although we can. If we leave the limit as x approaches 2 from the left of 3 over x minus 2, we'll get the same sort of result. We're going to get 3 over, in this case, The denominator is actually going to be negative, right? Because it's a number slightly less than 2 minus 2. So you're going to get a negative number. Positive divided by negative is negative infinity. So this still tells us we have a vertical asymptote at 2. Graphically, what this means is that at 2, there's our vertical asymptote. As we approach 2 from the right, we shoot up to positive infinity. As we approach 2 from the left, we go down to negative infinity. So our graph will look something like that, at least around 2. And then, yeah. We could also talk about the horizontal asymptotes here. So the big picture for asymptotes is that vertical asymptotes you get when the limit is equal to some sort of infinity as you approach a real number like 2 or 5 or negative 7. Whereas horizontal asymptotes are what you get when you take the limit as x approaches infinity. So we take the limit as x approaches infinity of 3 over x minus 2. Well, now we can see that the limit of this is going to be 0 because the denominator is getting very, very large and the numerator is just 3. Or more generally speaking, we know that when you have a rational function, if the degree on top is less than the degree on the bottom, which it is here, right, the degree on top is 0, there are no x's, the degree on the bottom is 1, then that limit's 0. And that's true whether we're going to infinity or if you go to negative infinity. So that means we have a horizontal asymptote of y equal to 0. So this graph is going to look kind of like this and like this. So that is very generally how we find asymptotes. Yeah, let me see. I know people ask some questions that seem kind of related. No, not that one. That one, sorry. Not that one. Okay. Sorry, just trying to look at all. There are people asking me quite a few questions about this stuff, so I'm trying to make sure I hit all the things. Sure. Let's look at a couple more examples. And I should point out, yeah, we'll do that. Okay, sure. So somebody asked about this question real quick, and I think this was just a typo or something that Thompson wrote incorrectly. She had written in her notes, the limit as h goes to 0, infinity, I think, of 2x squared over x squared was equal to 2. It doesn't, I mean, technically that is true, because if you simplify this, it's just 2 and it doesn't matter what h is doing. But I'm pretty certain what she actually meant to write was the limit as x approaches infinity of 2x squared over x squared is 2. Now, the thing about this one specifically is you can evaluate this limit by first simplifying this. 2x squared divided by x squared is just 2, right? No matter what x is, unless x is 0. But x isn't 0 because x is going to infinity. So that's just the limit as x goes to infinity of 2. And the limit of a constant is always the constant. So what does that tell me? This tells me that the function, which is kind of a weird function, but fine, 2x squared over x squared has a horizontal asymptote at y equal to 2. It's also just the function is 2, which is kind of weird, but okay. A better question would be, what about the function, say, 3x squared plus 1 over x squared plus 5? This function, we could ask about, does it have any vertical asymptotes? Does it have any horizontal asymptotes? So actually, let's ask the first question. Are there any vertical asymptotes? Does the denominator ever equal 0? Let's take a look. X squared plus 5 equals 0. I think the answer is no. Because if we try and solve this, we get x squared equal to a negative number. And we can't take the square root of a negative number and get a real result. So No vertical asymptotes. Does this function have a horizontal asymptote? Yes. If we take the limit as x goes to infinity of 3x squared plus 1 over x squared plus 5, I don't know how much work your teacher wants you to show, but we could use the shortcut and say, since the degrees are the same, right, it's a degree 2 on top, it's a degree 2 on bottom of this rational function. If the degrees are the same, the limit as x goes to infinity is the quotient of the leading coefficients, which in this case would be 3 over 1. The work your teacher might want you to show, I'm going to erase this part over here. Sometimes the work they want you to show is to divide everything by the highest power of x in the denominator. So I can write this as the limit as x goes to infinity, divide everything by x squared. So 3 plus 1 over x squared over 1 plus 5 over x squared. And then these parts go to 0. So you get 3 plus 0 over 1 plus 0, which is just 3. And this would be true whether we were going to infinity or negative infinity. So our horizontal asymptote would be y equal to 3. And that's how we find horizontal asymptotes, by taking the limit as x goes to infinity or to negative infinity. In this case, it would be the same either way. Let me give you, let's do one more that someone asked about. It's going to be slightly different. Is this pen good still? Sorry. I'm looking at good pens here. There we go. What else is going on? Yeah, so again, horizontal asymptotes, we take the limit as x goes to infinity. Vertical asymptotes, we try to find where the limit is equal to infinity. Really, with vertical asymptotes, you're just looking for where you might be dividing by 0 and not 0 on top. Someone wrote me a message. I'm not sure what WB, what do you mean? What about the 1 and 5? The 1 and 5. Oh, yeah, okay. So what happens here is, so we're dividing everything. So basically, the 1 and 5 don't really matter. Let me point, so let me plug in a value for x real quick. Let's say x was 1,000. So x is 1,000. 1,000 squared is 1,000,000. If I plug in 1,000, I'm going to get 3 times 1,000,000, so 3,000,000 plus 1, divided by 1,000,000 plus 5. So what we kind of say is the 1 and the 5 end up really not mattering or not contributing, because this part here is the dominating factor. The 3x squared and the x squared really overpower the 1 and the 5. So if I look at 3,000,001 divided by 1,000,005, I bet it's going to be pretty dang close to 3. So 3,000,001 divided by 1,000,005. Let me make sure I get enough zeros there. I'm getting 2.9999986. Pretty close to 3. But yeah, so what's happening in our actual work here is that we divided everything by x squared. So I've got 1 over x squared here. And then as x gets infinitely large, 1 divided by x squared gets infinitesimally small. So that's why we're saying these go to 0. Sometimes people will write out one more step, and they'll say that this is equal to 3 plus 0 over 1 plus 0, which is 3. But that's what's happening there. All right. Let's do one more, because there's one more kind of tricky type of limit, and let's do both sides of it. Let's first do the limit as x goes to minus infinity of the square root of 3x squared. Where'd you go? Sorry, 4x squared minus 5 over 3x plus 7. Okay, so here's the idea with this one. Yeah. If you have a chemistry review, you certainly should feel free to leave and go to it when the time comes. In fact, let me, before anyone leaves, not that it's close to 10 yet, but let me take a screenshot of all the names so I can do the attendance later. There's so many of you, which is good. I'm glad there's so many of you. Cool. All right. All right, got it. Let me do that. Okay, so when you have a limit like this, when you have a square, so basically this numerator part is acting like x, right? The square root of x squared, pretty similar to x. There's a little bit of a thing we have to deal with, but we'll deal with it. The bottom is also acting like x. So this is very much like a rational function. It's not a rational function because it's not a polynomial on top, but it's very much like a rational function where the degree on top is 1 and the degree on the bottom is 1. So we would expect the limit to be the quotient of the leading coefficients. But to get there, we have to be a little extra careful. So here's usually what people do. When you've got a square root of something x squared in the numerator or denominator, we like to factor out an x squared from inside the square root. So I'm going to rewrite this as the limit as x goes to minus infinity of the square root of, I'm going to factor out an x squared. So if I factor out an x squared, I'm left behind with a 4 minus 5 over x squared. And hopefully everyone's okay with that. I feel like it's a little too light in my room. In the bottom, I still have 3x plus 7. Let me fix my, sorry. Let me change that video. So yeah, I got my adjust. Yeah, that should be better. Okay. Hopefully that makes it a little easier to see the board now. So here's the thing. We're going to rewrite this numerator as, still have to write the limit. We have to write the limit every step until we actually take the limit. So I'm going to write this as the square root of x squared times the square root of 4 minus 5 over x squared. Over, I'm actually going to factor out an x from the denominator as well. You know, people don't always do this, but I find it easy to do this. So I'm going to do x times 3 plus 7 over x. Okay, this next part is the important part. What's the square root of x squared equal to? Well, it's not exactly x. It's actually the absolute value of x. I'm going to cheat and replace it with the absolute value of x here. All right, so this is where the magic happens. So here, not really the magic, this is where the important part happens. Here's the thing. If x is negative, and x is going to negative infinity, that means the absolute value of x is actually negative x. I can talk more about this if anyone wants me to. Probably will, even if you don't. The idea here is that, right, what's the absolute value of negative 6? It's negative negative 6. If the insides are negative, the way you take the absolute value is you make it the negative of that negative to turn it into a positive. That's what we're doing here. The insides are negative, right? X is going to minus infinity. So to make the whole thing positive, we take the negative of that negative number to make it positive. Okay. So then this x cancels with that x. And we're left with the limit as x goes to minus infinity of the square of negative square root of 4 minus 5 over x squared over 3 plus 7 over x. And then just like in the previous problem, the things divided by x go to 0. So 7 divided by a really, really negatively large number is going to go away. 5 divided by x squared, 5 divided by a really, really large number is going to get really, really small. So we're left with the negative square root of 4 minus 0 over 3 plus 0, which is going to be negative 2/3. To contrast this, if we took the limit as x goes to positive infinity, everything would be the same up until this point right here. But if we were doing the limit as x goes to positive infinity of the absolute value of x times the square root of 4 minus 5 over x squared over x times 3 plus 7 over x, then since x is positive, the absolute value of x is just x. So we have the limit as x goes to infinity of x times the square root of 4 minus 5 over x squared over x times 3 plus 7 over x. the x's cancel, and here we end up getting a positive 2 on top, right? We plug in infinity, this part goes to 0, this part goes to 0. We get the square root of 4 minus 0 over 3 plus 0, which is 2/3. So this particular function, the square root of 4x squared minus 5 or 3x plus 7, actually has two different horizontal asymptotes. It has a horizontal asymptote of negative 2/3 as we go to the left, and positive 2/3 as we go to the right, which is interesting. That's the most horizontal asymptotes a function can have, is two different ones. Okay, I think I've talked about asymptotes enough. Let's kind of move over to talking about continuity. Let's see, sure, people had questions about that. Oh, I was gonna do, yeah, that's actually, sorry, I got one more, but it actually kind of is going to segue into continuity, so I think it's a good example. So I want to know about this function, f of x equal to x squared minus 4 over, sure, 2x squared minus 50. I want to know what my vertical asymptotes are, what my horizontal asymptotes are. So vertical asymptote, well, actually, let's do horizontal asymptote first. So yeah, I'm definitely moving towards definition of the derivative kernel for sure. So horizontal asymptote here, again, degree on top, degree on the bottom, the same. So I'm going to take the shortcut and just say the horizontal asymptote is 1/2, right? It's the quotient of the leading coefficient on top divided by the quotient of the leading coefficient on the bottom, as long as the degrees are both the same highest power, which they are in this case. The vertical asymptote, we're looking for where the denominator is not, sorry, where the denominator is 0 and the numerator is not. So here I'm looking for where 2x squared minus 50 is equal to 0. To solve that, I would probably factor. So let's say this is going to be 2 times x squared minus 25, which is 2 times x minus 5 times x plus 5. So I get x equal to 5 and negative 5. Those are my vertical asymptotes. And I should point out that both of those are where the denominator is 0 and the numerator is not 0. So those would be the vertical asymptotes, those would be the horizontal asymptotes. I want to do one that's similar to this, but it's a little bit different. Actually, let me ask one more question. Where is this function discontinuous? Well, it's a rational function. Rational functions are continuous on their domains. This function is defined everywhere except for where it's not. I know that seems very kind of self-referential, but what I mean is this function is defined everywhere except for where the denominator is 0. So this function is discontinuous at x equal to plus or minus 5. And if we were to graph this, I don't know what the graph looks like exactly, but it's going to look something like, got vertical asymptotes at 5, negative 5, got a horizontal asymptote at 1/2. It's going to look something like this. Sure. And one of the reasons I'm graphing this is to speak to what kind of discontinuity this is. So these discontinuities are just asymptotic discontinuities. I don't think there's another way to really describe them. But they are definitely non-removable. So a removable discontinuity is one where if you can put one point back in, it makes the function continuous. This one clearly, right, we couldn't just put a point in there and make it continuous, right? It still would be discontinuous because you still got this weird kind of big jump thing happening. I want to contrast that with the next example. Let me see, how do I want to do this one? Yeah, sure. So let me ask, where is this function? X squared minus 9 over X squared minus 4x plus 3. Where is this function discontinuous? And what kind of discontinuities? All right, so again, rational function. Rational functions are discontinuous where they're undefined, meaning where the denominator is 0. So let's take a look. So I've got x squared minus 4x plus 3. I'm going to factor this as x minus 3 times x minus 1. So this is discontinuous at x equal to 3 and x equal to 1. Now, what kind of discontinuities are these? Well, if we try, well, in fact, really we should take the limit, I guess. So if we look at the limit as x approaches 1, and let's pick a one-sided limit just so we don't get some weird, like, whatever. Do one from the right. On top, I've got x squared minus 9, which I'm going to factor as x minus 3 times x plus 3. And in the denominator, we know it factors as x minus 3 times x minus 1. These parts cancel, right? They're not even important. And if we plug in 1 from the right, I get 4 on top. I get a positive number on the bottom. A positive small number, meaning this goes to some sort of infinity. So at 1, the type of discontinuity we have is a vertical asymptote, which is non-removable. At x equals 3, we have something different. So we take the limit as x approaches 3 from either side, although it's going to be the same on the other side. This one wouldn't be the same on the other side. This one would be positive infinity on one side, negative on the other. But if we approach 3, say from the right of this same expression, well, again, the x minus 3's cancel. If we plug in 3, we get 3 plus 3 over 3 minus 1, which ends up being 3, coincidence. But here's what this means. This means that we have a hole at x equal to 3. If you're, in fact, this graph, if you were to graph it, has a vertical asymptote at 1, would have a horizontal asymptote at 1 because the degrees are the same and the coefficients are both 1. And then would look something like this. Except at 3, so 1, 2, 3, there's a hole at the point 3, 3. And that hole, that's an example of a removable discontinuity. Because we could, so basically what we could do is we could redefine the function and add in that 1 point. So this function is discontinuous at x equal to 1 and x equal to 3. But if we wanted to redefine it, right over here, say, well, I'm going to add back a point in. I'm going to say f of x is equal to that, x squared minus 9 over x squared minus 4x plus 3, when x is not equal to 3, right, because it's undefined at 3. And then I'm going to define it to be 3 when x is equal to 3. Now this function is continuous at 3 because we added back in the 1 point that was making it discontinuous there. Whereas at 1, we cannot add that back in. The reason we have an open circle at 3 is because basically, so what happens if we plug in 3 to this function? We get 9 minus 9 over 9 minus 12 plus 3, or 0 over 0. And whenever you have a 0 over 0, you have a hole there because it's totally undefined, right? 0 divided by 0. But what's happening is that for values of x that are close to 3, right, as x is closer and closer and closer to 3, well, these parts are equal to each other, right? If x is like 3.00001, this is 0.00001 divided by 0.00001. Those cancel and just divide out to 1. And then the remaining part is this number that's very, very close to 3 plus 3, which is 6, and this number that's very, very close to 3 minus 1, which is 2. So from either side, as x gets closer and closer to 3, the y values also get closer and closer to 3. But at 3, totally undefined. And more generally, when you have a 0 over 0 type of thing happening, your graph is going to have a hole, which is a removable discontinuity. Okay. Let's talk a little bit more about discontinuity. I would definitely encourage everybody to look at your, so I finished grading your quizzes this morning. You should definitely look at the comments. You should also really, really look at the solutions I posted on Canvas. A few of you got all the things right about continuity, but most of you missed at least one thing about where the function was discontinuous. So I really strongly encourage everyone to look at those and to kind of see how the function was discontinuous at 1, how it was discontinuous at 3, and how it was discontinuous at 5. Well, let's look at another example here. Where'd you go? Excuse me, sorry. Yeah, sorry, one sec. So let's look at this function. Okay, f of x equal to the piecewise function. What time is it? Okay, yeah. 3x plus 1 when x is less than or equal to 0. 2x plus 5 when x is between 0 and 1. 8 when x is equal to 1. And I don't know, the square root of x plus 48 when x is greater than 1. There shouldn't be equal to there, sorry. Can't be equal to two different things. There we go. So here's a function, and we're interested in talking about, is it continuous, or where is it discontinuous? And so this function, continuous everywhere it's defined. This function, continuous everywhere it's defined. This is just a straight, horizontal line. And this is continuous on its domain, which is everything from negative 48 to the right. So certainly when x is bigger than 1, definitely continuous. So the only places we're concerned about where it might be discontinuous are where we're changing from here to here, or from, at 0 or at 1. So let's talk about 0. What's f of 0? Well, f of 0, I look at where x is equal to 0, and then I use the corresponding piece of the function. So f of 0 is going to be, the last part says the square root of x plus 48. Yeah, I wrote that kind of small. So for f of 0, I'm going to pick this piece of the function, go for x is equal to 0, and you get 3 times 0 plus 1, which is 1. Now let's talk about the limit as x approaches 0. Right? So, because there's three things. If you're talking about continuity, you want the function to exist, you want the limit to exist, and then you want them to be equal to each other if they both exist. So for the limit as x approaches 0, since it's defined to be something different on the left of 0 and the right of 0, we're going to look at those ones. Now, a couple people I saw when they were doing this kind of problem on the quiz, when they did the limit as x approaches 0 from the right, they picked like one of these other pieces. We have to pick the part where x is bigger than 0, but still close to 0, right? I know x is bigger than 0 here, but we need to pick where we're just next to 0. So for the limit as x approaches 0 from the right, we're going to use this piece of the function, because that's where x is bigger than 0. I'm going to plug in 0 for x, because right, we evaluate limits by just throwing x in, the x value in if we can. I'm going to get 0 plus 5. On the other hand, the limit as x approaches 0 from the left, well, then I'm going to use this piece of the function, because that's where x is less than 0. And if I plug in 0 here, I'm going to get 1. The limit from the right and the limit from the left are not equal. So this means that the limit as x approaches 1 of f of x does not exist. And this is an example of a jump discontinuity, which is non-removable, right? You can't, So right, basically what's happening is if you try and graph this, right, the left side is approaching 1. So we got something like this. And then the right side is approaching 5. So it's something like this. Right, there's a big jump there from there to there. There's no way we can put 1 point back in and make it continuous. So this is another example of a non-removable discontinuity. There's no way
James?
Yeah, go ahead.
Shouldn't it be the limit as x approaches 0 does not exist instead of x approaches 1?
Yeah, you're right. I'm sorry. Thank you. Yeah.
Yeah, and then it should be f of 0, right?
No. So when I write this, I write the limit x approaches 0 of f of x does not exist.
Right, but I just meant above the calculation that you did where it says f of 1.
Oh,
right
this does say f of 0. I know.
That's
1, but it actually
okay.
0 there. My 0
Thank you.
is terrible. Yeah, that's a 0. But yes, you're totally right. I definitely should be right. That's the limit x approaches 0. Yeah. Good call. Thank you. Please always, if you see an error, let me know right away. So we can stop there. It's discontinuous. What about x equal to 1? Well, f of 1, and definitely people got a little bit caught up with a similar example in the quiz. F of 1 here, we have to use where x is equal to 1. F of 1 is just 8, right? There's no x there. There's just, it's 8. So then what about the limit? So the limit as x approaches 1 of f of x, well, let's do both sides. Limit x approaches 1 from the left. So that's where x is less than 1. So I'm going to use this piece of the function. That's going to be the limit. Yeah, I should have enough room. Limit as x approaches 1 from the left of 2x plus 5. I'm going to just plug in 1 for x and get 2 times 1 plus 5, which is 7. Limit as x approaches 1 from the right. So I have to use where x is bigger than 1, which is this piece here, not this piece here. So I have to use that. So it's going to be the square root of x plus 48. I'm going to plug in 1. 1 plus 48 is 49. Square root of 49 is 6. Wow. Oh my God. I was thinking of the other problem. I don't know how I just said that. Please forget I ever said that. Erase it from your memories. I might edit it out later. Square root of 49 is what? 7. There was another, I know, I do feel great shame. I was thinking of the quiz problem where there was a square root of 36. Anyway, still doesn't, yeah. You got to think of what you're doing on the board, not with something else. So yeah. Anyway, the limit is 7 here, right? The limit from the left is 7, the limit from the right is 7. So the limit as x approaches 1 of f of x is equal to 7. Now, a few people did say for the similar quiz problem, when they found the limit was what it was, they said the function was continuous. But it's not. Because to be continuous, the limit has to equal what the function's equal to. And these are definitely different numbers. So this function is discontinuous at x equal to 1. And the reason is, I'm going to erase over here because I'm kind of out of the room. The reason it's discontinuous is because, so we're discontinuous at x equal to 1 because the limit as x approaches 1 of f of x does not equal f of 1. Right? This is 7. This is 8. I will also mention this is the type of discontinuity that is a removable discontinuity. Right? If the limit exists and the function exists, but they're not the same, that can always be changed. Here's what this looks like graphically. Sure, I guess I can try and draw it up here again. So graphically what we have happening is that, so here's 1. On the left side of 1, we're getting close to 7. So here's 7, here's 8. So on the left side of 1, we're coming at 7 like this. On the right side of 1, we're coming at 7 more like a square root. So maybe something like, I don't know, like this. But then at 1, the function is equal to 8. So we have a point discontinuity where if we decided to, right, we could redefine the function to be equal to 7 there. And that would make it continuous. So that's an example of a removable discontinuity where if you fix just one point, you can make it continuous. Okay. Yeah, so just to kind of sum up continuity, because definitely continuity is a big deal. To check if a function is continuous at x equal to a, there are three things to check. One, f of a must exist. Two, the limit as x approaches a of f of x must exist. Usually, especially for piecewise functions, this requires checking that the left and the right hand limits are the same, right? So the limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. And then finally, they have to equal each other. The limit as x approaches a of f of x must equal f of x. Those three things are true, then your function is continuous at a. Correct, Gabriella. Right. As soon as one of these things is not true, you're done. You should stop and say discontinuous. Yeah. I will also point out that, yeah, let me actually do this here. The other thing to be aware of is polynomials are continuous everywhere. So anything that just has positive integer powers of x is going to be continuous everywhere. Someone asked me, oh, I think I didn't actually write it down, but someone asked a question like something like, the function I was given was what interval is something like 2x cubed plus 5x plus 8 continuous on? It's continuous on the entire interval because polynomials are all continuous everywhere. And then things like rational functions are continuous on their domain. So except for where you're dividing by 0, a rational function is continuous everywhere else. So those are a couple important ones to remember. And then I think we also talked about, at least I think I said last time, sine of x and cosine of x are continuous everywhere. So is e to the x. I'm just going to say they're continuous, meaning they're continuous everywhere. And then the other trig functions, tangent, cotangent, secant, cosecant, and also throw in natural log of x for good measure. Those are all continuous where they're defined. So they're continuous on their domains. So for natural log of x, it's continuous as long as x is positive. And for the rest, tangent, cotangent, secant, cosecant, continuous wherever they're defined. So I know like tangent, right, is undefined at pi over 2 and 3 pi over 2, right? It's got all those vertical asymptotes. It's continuous everywhere else, just not at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on and so on and so on. Same is true for cotangent, secant, and cosecant. And just to kind of roll back around to Gabriella's statement there, I would say it's discontinuous, but I would say it's discontinuous at x equal to a, not at f of a, because maybe f of a doesn't even exist. So right, if you're missing one of these three, it's discontinuous at x equal to a, if any of these fail. All right. Let me take a look at my list here. I think I'm getting through things. Okay, cool. Let's go ahead and move on to talking about derivatives and the limit definition. Yeah. Oh, there was. Yeah, cool. Let me grab this question here. Not that one. Sorry, I've only got like 1,000 things up. Sure. So here's a good example to start with that somebody asked me about. In addition to talking about using the limit definition, we will also talk about what it means for a function to be differentiable and not differentiable. So here is a question from section 2.1. Consider the function y equal to g of x equal to negative x squared plus 9x plus 5. And the first part of this question is to use the limit definition to find the derivative. So find g prime of x using the limit definition. I'm gonna say this pretty strongly here. If you have a test or exam and they say to use the limit definition, if you use the power rule here, so in case you don't know, which is fine if you don't know the power rule yet, but we're gonna find a very easy way to take this derivative later on. The derivative is gonna be negative 2x plus 9. But if you just use the power rule and they say use the limit definition, you're probably gonna get almost no credit. Now, if you don't remember the limit definition, it's still not terrible to write down what the answer is, knowing via another rule, but just be aware, right? If it says use the limit definition of the derivative, we have to do the limit as h goes to 0 of g of x plus h minus g of x all over h. Or if your teacher is using delta x, it's the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. Same difference either way. I don't love this for a couple reasons. One, it's more writing. Two, it's easy to accidentally kind of forget there's a delta there and accidentally cancel an x that's attached to the delta x. So I'm going to write it like this because I find it to be better. But you should write it whichever way you're most comfortable with, or whatever way your teacher wants you to write it. Okay. The game plan for this, always. This needs to cancel. That is always the ultimate goal. Make that denominator cancel. The intermediate goal, almost always really, is, okay, if I want to make this h cancel, I need everything in the numerator to have an h so that I can factor it out and cancel the factored out h with the denominator h, or the factored out delta x with the denominator delta x. So our intermediate goal is always to cancel all the non-h terms in the numerator, or the non-delta x terms in the numerator. So we have to write out what this is. And this is where it's really easy to make errors. So in fact, I think it's worthwhile, if I've got this already, which we should, because you can't really do the problem if they don't give you a function, it's probably not a bad idea to just say, okay, well, g of x is that. G of x plus h is going to be minus x plus h squared plus 9 times x plus h plus 5, right? I'm just saying g of a thing is minus the thing squared plus 9 times the thing plus 5. And here the thing, instead of being x, is x plus h. So g of x plus h is minus x plus h squared plus 9 times x plus h plus 5. So let's write it all out. It's going to be a little messy. So first, g of x plus h, that's all that. It's minus x plus h squared plus 9 times x plus h plus 5 minus all of g of x. And it's minus all of this, so you have to have parentheses. Minus x squared plus 9x plus 5, all divided by h. And then we have to simplify. A couple things to be aware of. The two most common mistakes are not distributing this minus sign, so we have to distribute the minus sign, and multiplying this out incorrectly. Let me actually do that on the other side here just real quick. So you're going to see x plus h squared or cubed, but often squared. You're going to see x plus h squared a lot. So it's really, really vital that you know that x plus h squared is just x plus h times x plus h, which we're going to FOIL out, and we're going to get 3 terms. Well, 4 of them we're going to combine. We're going to get x times x times h times x, and h squared. X times h plus x times h is 2 times x times h. This is x squared plus 2xh plus h squared. And I want to really, really stress, this is not x squared plus h squared. When you multiply out x plus h quantity squared, you're always going to get a middle term. So be careful, because that middle term is really important. Actually, that middle term is where the right answer is kind of coming from. So we have to get this. Okay, so here's what we've got. We've got the limit as h goes to 0 of minus x plus h squared, which is, we just said x squared plus 2xh plus h squared. Observe that we still need to distribute the minus sign after we do this, right, after we do that part. We have to distribute the 9 here. So we get 9x plus 9h plus 5. And then we have to distribute this minus sign to each of these three terms. So minus a minus is plus x squared minus 9x minus 5. All divided by h. Okay, let's cancel what we can cancel. So the 9x and the minus 9x cancel. The 5 and the minus 5 cancel. I can't quite cancel this x squared yet because I should distribute this minus sign first. So this is going to be the limit as h goes to 0 of, let's see, negative x squared minus 2xh minus h squared plus 9h plus x squared all over h. And now I can cancel the negative x squared with the positive x squared. And look, everything that's left in the numerator has an h in it. Minus 2xh minus h squared plus 9h. You can, at this point, divide each thing by h. But to be more careful, I'm going to factor out an h. It's perfectly fine to skip this step. But I'm going to factor out an h and say I've got h times negative 2x minus h to the first plus 9, all divided by h. Then this h divided by that h divided by h is 1. And then I can take the limit as the rest of the h's go to 0. So I get negative 2x minus 0 plus 9. And that's my derivative, negative 2x plus 9. Which is what we would have gotten using the power rule, but this is what they asked us to do. I will point out that this function is differentiable everywhere because the derivative, which is negative 2x plus 9, is continuous everywhere because it's a polynomial, right? The derivative is a polynomial, which is continuous everywhere. So if your derivative is continuous, that means your function is differentiable. So this function is differentiable everywhere because the derivative is continuous everywhere. Also, polynomials are always differentiable everywhere. It's great. Polynomials are like the best ever. They do all the things we like. There's a couple more questions to this question. Determine the slope of the tangent line of this function at the value x equal to 3. So go over here. Our function g of x, we just found g of x equal to negative x squared plus 9x plus 5. And we just found the derivative, using the limit definition, to be negative 2x plus 9. And now they're asking, what's the slope of the tangent at x equals 3? So slope of the tangent line at x equal to 3. So the derivative evaluated at whatever x is the slope of the tangent line at that value of x. So the slope of the tangent line is just going to be the derivative evaluated at 3, which in this case is going to be negative 2 times 3 plus 9, which is negative 6 plus 9, which is 3. Coincidentally, also 3. Just a coincidence, though. So the slope is 3. And then we're also asked to find the equation of the tangent line. So we have all we need. I want to find the equation of a line. In fact, let me graph this just so I can kind of give you guys an idea what's happening here. So negative x squared plus 9x plus 5 is a downward opening parabola. Let me think for 1 second. It's a downward opening parabola. Negative. Sure. Looks something like this. the vertex is occurring at 9 halves, comma, whatever. Don't really care. So over here is 3. And here's my tangent line. And we found the slope is 3. So I want to find the equation of the tangent line. I need the slope. Boom, done, got it. And I need a point. Well, the only point I have is the point where it's tangent at, which is where x is 3 and y is g of 3. Which I'm going to get by plugging it back in here. So g of 3 is going to be negative 3 squared plus 9 times 3 plus 5. Okay, we have to be careful here. This negative 3 squared is negative 9 because the squaring is happening before the negative since there's no parentheses. This is negative 9 plus 27 plus 5, which is 18 plus 5, which is 23. So to find the equation of the line, we're going to use the point slope form. And we're going to get y minus the y coordinate, which is 23. At that point there is 3 comma 23. So y minus the y coordinate equal to the slope times x minus the x coordinate. And you can probably leave it like this, or you can solve for y. You can say y equals, distribute the 3 here, 3x minus 9, and then add the 23. So we would get y equal to 3x minus 9 plus 23 is going to be 14. So that's how we find the slope of the tangent line. We find the slope using the derivative, we find the point using the function, and then we use the point slope form. All right. By the way, it is 10 o'clock. If any of you need to go to there's a chemistry review or something happening. If any of you need to go, you're certainly welcome to go. I'll miss you, but you're welcome to go. All right, so that covers that. Let's look at some more limit definition of the derivative questions. I know there was another one on here, yeah. All right, we got 20 minutes to do some stuff. So I'm gonna say a little bit more. I don't remember who asked this question, but the question was find the derivative of f of x equal to the square root of x plus 2 using the limit definition. And I'm going to tack on an extra question here. Where is this function differentiable? So a couple things to be aware of. First of all, a function can only be differentiable where the derivative, where the function is defined, meaning where it exists. And actually, there's a more stringent requirement. So f of x is only differentiable, is only possibly differentiable if the function is continuous. So to even have a chance at the derivative existing, the function has to be continuous there. Or as people more succinctly write, differentiability, which is a long word to write, implies continuity. So if you know a function is differentiable somewhere, it automatically had to have been continuous there. Why? Well, let's look at an example. Let's look at one, maybe two examples. Just some real kind of silly graphs that are obviously discontinuous. So let's look at a jump discontinuity. Like let's say we're looking at the point 2, and let's say we have a function that looks something like this, and then something like this. And I'm asking, what's the slope of the, so when we're asking what the derivative is at a point, in this case at 2, we're kind of asking, what's the slope of the tangent line there? Well, the slope of the tangent line needs to be the same from the left and the right. And the problem is the slopes of the tangent lines here, right? Tangent line, tangent line, tangent line. We're getting some value, but the ones on the right, right? They're not even, they don't even have a chance of being the same. Also, you can't really have a tangent line there. So it's a big problem if it's discontinuous, right? You have to have a function being continuous for the left and the right hand tangent line to kind of make sense that they would match up. So I don't want to get too in the weeds about this particular detail, but we are going to say, and maybe I'll say more about this next time when I've thought about it a time more. For a function to be differentiable, it had to have been continuous. Definitely need that to be true. So this function, square root of x plus 2, looks like the regular square root function shifted 2 to the left. So it looks like that. And it's definitely continuous on its domain. So this function is continuous on the interval from -2 to infinity. So we're gonna find the derivative, then we're gonna talk about where the function is differentiable. It can't be differentiable anywhere left of there because it doesn't even exist anywhere over there. So the derivative definitely can't exist for x less than -2. It just doesn't work. There is no function there. Well, let's go ahead and find the derivative using the limit definition. So we take the limit as, I'll use delta x this time just to do a delta x one, even though I don't love delta x. Limit is delta x goes to 0 of f of x plus delta x minus f of x over delta x. That's going to be the limit as delta x goes to 0. So again, we're taking our function and everywhere there's an x, we're putting delta x instead. Sorry, x plus delta x instead. So it's going to be the square root of not x plus 2, but x plus delta x plus 2 minus f of x, which is just the square root of x plus 2, all over delta x. And what we're going to do here is we're going to, whenever we have a square root minus or plus something else, we're going to multiply by the conjugate. So we're going to write this as the limit as delta x goes to 0 of the square root of, I'm going to drop the parentheses in there because I don't really need them, x plus delta x plus 2 minus the square root of x plus 2 all over delta x times the conjugate of this, which is the square root of x plus delta x plus 2 plus the square root of x plus 2 over the same thing. And the reason we multiply with the conjugate is because the things that are conjugates, you get rid of the roots. So when you multiply this minus this, you get the first thing squared minus the second thing squared. The middle terms cancel out. So we end up with the limit as delta x goes to 0 of the square root of x plus delta x plus 2 squared. So x plus delta x plus 2. Middle terms cancel, right? This times the square root of x plus 2 and this times the negative square root of x plus 2. Those add together and cancel out. And then minus this times that is minus the square root of x plus 2 squared, which is minus x plus 2. So we always multiply out the conjugates and get the first thing squared minus the second thing squared. The things that are not conjugates of each other, we don't multiply out because we know that we want this to cancel out. So there's no good reason to multiply it through. So we're going to write this as delta x times the square root of x plus delta x plus 2 plus the square root of x plus 2. And of course, I'm really out of room here. Sure. I can erase this stuff on top. So simplifying here, this is equal to the limit as delta x goes to 0 of x plus delta x plus 2 minus x minus 2 over delta x times the same denominator, square root of x plus delta x plus 2 plus the square root of x plus 2. And just like we want, all the non-delta x terms cancel out. X minus x cancels. 2 minus 2 cancels. I don't personally think it's a good idea to say these things cancel and then that cancels that in the same step. Some people like to. I kind of feel like it can be misleading to the reader. So if the limit is delta x goes to 0, I guess we can say delta x divided by delta x is 1. I mean, I just say I don't want to do it in the same step. I'm just not going to write that they cancel that. But I'm going to say, okay, we got delta x over delta x. That's a 1 over, so those cancel. Square root of x plus delta x plus 2 plus the square root of x plus 2. And then this delta x gets to go to 0. So we're left with, I think I can squeeze this in here, 1 over the square root of x plus 2 plus the square root of x plus 2, which is 1 over not x plus 2, but 2 times the square root of x plus 2. Right, these were multiplied together in the bottom, you get x plus 2, but since they're added, you get 2 of them. Okay, so now here's the question. We know that the domain of the original function, square root of x plus 2, is everything from -2 to infinity. But for the derivative here, we have almost the same domain, except -2 now is no longer any good. If I tried to find, I'm going to erase this. Actually, no, I don't want to erase this. I'm going to erase some of my derivative here because I think, sorry, I know it's likely it'll never. So my derivative, f prime of x, is 1 over 2 times the square root of x plus 2. And notably, f prime of -2, if we try and plug in -2, we end up getting 1 over 2 times the square root of 0, which is division by 0, undefined. Well, if the derivative is undefined, that means it's not continuous, which means that it can't be differentiable at that point. And what's really happening here is division by 0 means we've got some sort of infinity, right? So at -2, the derivative has an infinite slope or a vertical tangent line. So if we look at this here, right? I know I didn't draw this super great, but if you look at the tangent lines, right? So like at -1, it's like that. And as you get closer and closer to -2, the tangent lines get steeper and steeper and steeper. And when you get to 0, the tangent line actually is a vertical tangent line. And a vertical line has an undefined slope. So a vertical tangent line means the derivative is undefined. So this function is not differentiable at 0 because there's a vertical tangent line at 0. I'm sorry, not differentiable at -2 because there's a vertical tangent line at -2. And that would be true in this function where you have, right, where it kind of ends there, or in this very similar but different function. Yeah. So how do we show that f of x equal to the cube root of x is not differentiable at x equal to 0? Well, we could draw it. Here's what the cube root of x looks like. I've kind of exaggerated the verticalness of it, but it definitely has a vertical tangent line at x equal to 0. You could take the derivative. Now, the thing about taking the derivative here is using the limit definition is actually quite complicated if we want to take the derivative everywhere. You can either, 1, use the power rule if you've learned it. If f of x is x to the 1/3, f prime of x is 1/3 times x to the -2/3. And if we rewrite this, that's 1 over 3x to the 2/3. Try plugging in 0 there, it's undefined. But we might not have that yet. So how, if someone asked you on the test to show that this function had a place where it's, the derivative is undefined at 0, well, how do we do that? Well, we can find the derivative at 0. So instead of trying to find f prime of x equal to the limit as h goes to 0 of f of x plus h minus f of x all over h, we can say, well, I just want to find the derivative of 0, or really show it doesn't exist. So I'm going to look at f prime of 0, which is the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. And this is actually really easy to deal with. So f of x is the cube root of x. So f of 0 plus h is the cube root of 0 plus h, which is just the cube root of h. F of 0 is 0, right? The cube root of 0 is 0, divided by h. Well, look at that. That's super easy to simplify. This is going to be the limit as h goes to 0 of h to the 1/3 over h. But when you have division like that, you subtract the powers. 1/3 minus 1 is negative 2/3. This is the limit as h goes to 0 of h to the negative 2/3. Now be careful. If you plug in 0 here, you might convince yourself that 0 to the negative 2/3 power is 0. It's not. 0 to a negative power is undefined. I always recommend, if you find yourself with a 0 to a negative power, rewrite it as 1 over h to a positive power. So then you see, oh yeah, 0 to the 2/3 is 0, but 1 over 0 is undefined. But if the limit doesn't exist, well, the derivative is defined to be this limit. So if the limit doesn't exist, the derivative doesn't exist at 0. So here is another way a function is not differentiable. I mean, it's the same kind of way. We have a vertical tangent line. The derivative ends up being division by 0, which makes your value go into infinity. Got 5 minutes left. 2 other ways functions can be not differentiable are with what I like to call pointy points. I know it sounds kind of silly, but pointy points are where functions are not differentiable. The 2 kind of classic examples of pointy points where a function is not differentiable are the absolute value function. In fact, let's make the absolute value of x minus 2. Just to be a little more interesting. This function has a corner at x equal to 2. It is not differentiable there. And the reason it's not differentiable is because, again, the limit definition of the derivative is not going to exist there. If you try, in fact, we'll do it in a second. We have enough time, yeah. The other type of way a function can be discontinuous is if we have a cusp. So like f of x equal to x minus 2 to the 2/3 power, which looks kind of like this. So in each of these cases, the limit on either side of the limit definition of the derivative on either side are approaching different things. So here on the left, the slope is definitely -1. Here on the right, the slope is +1. But the limit from the left and the limit from the right are not going to match, which means the derivative is not going to exist because the derivative is the limit as x approaches, or as h approaches 0 thing. So here we have a cusp at x equal to 2. And I just call them pointy points. Cusp, corner, I don't really differentiate between them. Here, the only difference kind of really is that for a corner, right, you kind of just have no like derivative. Like the left side is one thing, the right side is the other thing. For a cusp, here on the left side, the derivatives are getting, well, the tangent lines are getting very, very steep, but they're negative. Sorry, I'm going to make my hand look like it. Right, it's a very, very vertical line. So the limit from the left is actually going to negative infinity. The limit from the right is going to positive infinity. Infinity is a problem anyway, but they're also not approaching the same sort of infinity. So both of these are discontinuous for those sorts of reasons. If you wanted to show that this function was discontinuous at 2, so to show that f prime of 2 does not exist, here we really are stuck using the limit definition. Yeah, and we've got enough time. I can make this happen. So let's say I want to find f prime of 2. Well, or show it doesn't exist. F prime of 2 is the limit as h approaches 0 of f of, instead of x plus h, it's going to be 2 plus h. minus f of 2 all over h. Right, I'm just replacing the x's in the limit definition of the derivative with 2's. Okay, but now I'm going to actually use the function. Absolute value of 2 plus h minus 2. Well, if I'm plugging in 2 plus h for x, 2 plus h minus 2 is just h. So I've got the absolute value of h. And f of 2, well, 2 minus 2 is 0, and the absolute value of 0 is 0, divided by h. But this limit, to see if it exists, I need to look at each side. So if I look at, I've got enough room, the limit as h approaches 0 from the right-hand side of the absolute value of h over h. Well, if h is positive, the absolute value of h is just h. So that's the limit as h goes to 0 of h over h, and h over h is 1. The limit of 1 is 1. Which makes sense, because when we're on the right-hand side, the slope is positive 1. On the other hand, if we do the limit as h approaches 0 from the left of the absolute value of h over h, well then, h is negative, which means the absolute value of h is negative h, right? Because you have to turn that negative into a positive. This is the limit as h goes to 0 from the left of negative h over h. And when you divide those, you get negative 1. So you get the limit as h goes to 0 of negative 1, which is negative 1. So the reason this example, this corner, is not differentiable is because the derivative doesn't exist there. I know that's kind of, silly, but specifically, the derivative doesn't exist because in the limit definition of the derivative, the limit doesn't exist because the left-hand limit and the right-hand limit are not the same. The left-hand limit is negative 1. The right-hand limit is positive 1 because the slope on the left is negative 1. The slope on the right is positive 1. So that is why corners often are not differentiable, because the right-hand derivative and the left-hand derivative aren't matching. And the same is true about cusps. Cusps are not differentiable for really kind of two reasons. The left and the right limits aren't matching up, and they're also both going to infinity. Why is it as h approaches 0? Because that's our limit definition, right? If I was trying to find, right, h is like my delta x. If I was trying to find the derivative, in general, the derivative would be the limit as h goes to 0 of f of x plus h minus f of x all over h. It's just that in this particular example, instead of doing f prime of x, we were doing f prime of 2. But it's still the same, everything's the same, except I've replaced the x's with 2's. But I could have written it, Gabriella, as the limit as delta x goes to 0. If I wanted to do f prime of 2 of f of 2 plus delta x minus f of 2. Right, I'm just using h instead of delta x, but it's still the same sort of thing.